This is Unit 8, Chemical Bonding, Part 1 Notes. By the end of this unit, you should be able to describe and explain the nature of metallic bonding and metallic properties. You should also be able to differentiate between an ionic and a covalent bond. You should also be able to name and write the chemical formulas of ionic bonding. So metallic bonding occurs within metals, and only metals. They're made up of metallic bonds. These are the forces of attraction between the free-floating electrons and the positively charged metal ions. There are few electrons located in the highest energy levels of your metallic atoms, and these outer levels are then considered mostly empty space. So whenever you have multiple metal nuclei overlap, the outer electrons are then free to move between the atoms. And the free-moving electrons are known as what is delocalized electrons. These delocalized electrons, they don't belong to a single atom, so they can move in between multiple nuclei. Metallic bonding is known as the electron C model, and it's depicted in this picture below. And if you open up the PowerPoint within the notes for Unit 8 folder in the forms and documents on my website, it will show you that the orange electrons are going to be free floating or moving throughout this entire lattice. So the electron C model are where atoms of a metal are somewhat fixed, so the nuclei position, the blue circles, are fixed in a crystal lattice. It is a complete geometric arrangement structure. It's just like the solid particulate diagram, and the outer electrons are able to then move freely through this lattice, and it forms what is known as the sea of electrons. And I'll show you during the lecture that we have in class, but the electrons are moving from nuclei to nuclei because of those overlapping empty orbitals. And because the electrons are free to move, this is where the metallic properties come into play, such as malleability, being able to be molded, conductivity, whether it's electrical or thermal, and then ductility, where you can draw the metals through a wire. Ionic bonding, on the other hand, is a compound that's composed of cations and anions. As we said before, cations are always going to be the metals, so metals always form positive charges. And your anions are going to be your nonmetals, and then these are going to form negative charges. So ionic bonding is between a metal and a nonmetal. These ionic bonds, again, are just the electrostatic force that holds the ions together within an ionic compound. So again, we have an attraction of a positive and a negative. In this case, it's the metal cation and the nonmetal anion, compared to the metallic bonding, where you are looking at just specific atoms, the positively charged nucleus of the metal, and then the electron of that same metal. But ionic bond is between a metal and a nonmetal, formed by ionic bonds. These are electrically neutral because the positive and the negative charges are always going to cancel out. So, for example, in your sodium chloride, we know that sodium is in group number 1. They form mostly +1 charges, and they lose this outer orbital, that one electron in the 3s orbital, to form a +1 charge. And then we have a chlorine, group 7. They normally form a -1 charge. So we're going to fill that outer orbital from a 3p5, add that one electron, and then we'll get a 3p6. And I've said before, atoms form charges because they are more stable, because they have a full octet, whether it's on the level below for your positive ion, or if it's on that same level for your anion. So the fact that sodium forms a +1, chlorine forms a -1, the plus and the minus will cancel out to become electrically neutral. But where does the electron from sodium go? Well, that electron goes from sodium whenever it's lost to the nonmetal, so it transfers those electrons, and eventually they'll form the sodium chloride compound, where sodium and chlorine will make a bond in this sort of fashion, and we're going to go into detail over Lewis dot structures later on, but there should be a full octet of electrons around chlorine. I know I drew too many dots around chlorine, but those should only be 8. But whenever they form that compound, the electrons are transferred from the cation to the anion, and that's important to know. So bonds are formed through the transfer of electrons from the metal to the nonmetal, or the cation to anion. And then the sodium chloride, they're going to make a compound in the same form as a crystalline-like lattice. It looks like a solid, particulate diagram of a solid. Okay, so you should be able to write an ionic formula. And to write an ionic formula, we need to know, first of all, that it's an ionic compound, because we see both a metal and a nonmetal. So we see a metal in a nonmetal. Metal is a cation, nonmetal is your anion. Cations are always written first. That's an extremely important rule. Always write the metal first. Once we identify the charges, we will cross and drop the numbers, so we leave behind the charges or assume the absolute value of the charge, so everything's going to be positive, and then we will reduce subscripts to the lowest whole number ratio. So writing the formula for the following ionic compounds, all these examples will have a metal and a nonmetal, and the metal will be written first. So lithium is first, the chlorine or the chloride ion is going to be written second. That's your nonmetal. Okay, looking at a periodic table, make sure you have those out, please. And then make sure you're able to climb your mountain of charges to identify the charges for group 1 elements. That is going to be something that you have to know. So you have to make sure you're able to identify charges for your group A representative elements. The symbol for lithium is Li. It's in group 1, so it forms a +1 charge. Your chlorine is in group number 7 with the symbol Cl, forms a -1 charge. So whenever you cross and drop the 1, we leave behind the charges. So the 1s will cross over, and 1s are understood. So your formula for lithium chloride is Li1Cl1, but you don't have to write the subscripts for the number 1. So completely, the formula for lithium chloride will just be LiCl. Going into number 2, the symbol for magnesium is Mg. It's in group 2, so it's a 2+ charge. The symbol for bromine is Br. It's in group number 7 with a -1 charge. So again, we cross and drop the numbers. We leave behind the charges, so this 1's going to cross over to be the subscript of magnesium. The 2 is going to cross over to be the subscript of the bromine. So we end up getting a formula of MgBr2 for magnesium bromide. Again, the 1s are understood and you don't need to write them. So pretty much the charge becomes the subscript of the other atom. Okay. Well, what if you have a situation where you have the same charges? Well, calcium symbols in group 2 has a 2+ charge. Oxygen, or the oxide, is group number 6, so it has a -2 charge. So whenever you cross and drop the numbers, each of the 2's are going to become the subscript. So you'll have a formula Ca2O2, but step number 3 says we need to reduce the subscripts to the lowest whole number ratio. So if you can reduce the subscripts by the same number, you do that. So you get CaO for the ionic formula, calcium oxide. Aluminum phosphide. Aluminum is in group number 3, so it has a 3+ charge. The phosphide, or the P, is in group number 5, so it has a -3 charge. If you cross over your 3's, you get Al3P3, so that should reduce out to just AlP, because we're supposed to reduce the subscripts to the lowest whole number ratio. So in the previous slide, we had metals that were from group 1, group 2, or group 3, and we should know those charges by being able to climb our mountain of charges. But what if we have a transition metal? I said to you guys, we don't know the charges because they can form multiple oxidation states based on the type of compound that they form. So for transition metals, they have a slightly different rule where when they have multiple oxidation states, their charge has to be identified with a Roman numeral. So just to review Roman numerals, we have Roman numeral number 1, then you have 2, that's Roman numeral number 3, IV is 4, V is 5, VI is 6, and then VI is 7, VI is 8, and you probably won't go above 5 or 6. But if you know at least 1 through 5, you should be able to identify charges for the majority of the transition metals. So for the first example, these are ionic compounds because I see a metal and a nonmetal. The symbol for iron is Fe, but we know that iron can form different charges. But this Roman numeral number 2 says it forms a +2 charge. So we have to get the charge of your transition metal from the formula. The fluoride, again, that's in group number 7, so they form a -1 charge. Crossing and dropping your charges, the 1 drops over here, the 2 is the subscript of the other one, so you just get FeF2 for the formula. Okay, so then iron 3, Fe, this Roman numeral 3 says it forms a 3+ charge. Your bromine is in group number 7, so it forms a -1 charge. you cross and drop the numbers. So then you get FeBr3 in this case. So this is the difference between iron forming a +2 or iron forming a +3 based on the Roman numeral. Then you also have copper 2 sulfide. The symbol for copper is Cu. The Roman numeral 2 says it's a +2 charge. And then the sulfide, that's sulfur in group number 6, so it forms a -2 charge. So you cross and drop your 2's. So we get Cu2S2, but don't forget the rule where you reduce the numbers to the lowest whole number ratio. So you get Cu1S1 for copper 2 sulfide, but the ones again are understood. So now we're going on to what is known as polyatomic ions. The prefix for poly means more than one, and every ionic formula that we've been writing dealt with monoatomic ions. So the difference between the monoatomic ions, where we had F-1, Br-1, S2-, those are all single atoms. That should be Br. But polyatomic ions are composed of multiple oxygens. So if you look at the following phosphate, sulfate, and nitrate, you see multiple oxygens within the anion. So that is a PO4 with a -3 charge. So the difference between a phosphide, which we're going to go over naming rules on the next lecture, but just to kind of preview, the IDE tells me that it's a single monoatomic ion, but your phosphate is a P, one phosphorus with 4 oxygens with a complete -3 charge. And just to be able to write those formulas is what we're trying to do today. We'll learn all the naming rules on the next lecture, and then we'll have a flow chart with that. But it follows the same rules for writing those formulas. You just have to drop the charge on the outside of that polyatomic ion. So for example, sodium, symbol Na, group number 1, so it's +1. The phosphate is a PO4 with a -3 charge, so this 3 is going to drop over to sodium, and the understood 1 is going to drop on the outside of the PO4. Ones are understood, so the total formula for sodium phosphate is going to be let me get more space, so I'm going to erase this. So we're going to have Na3PO4. Ideally, you'll have a parentheses around the PO4 if the number outside is something other than the number 1, but the 1 is understood, so it's just Na3PO4. For magnesium sulfate, however, magnesium has a 2+ charge because it's in group number 2, the -2 charge and the +2, so the 2's are going to cross over, and we reduce out the 2's, so ideally the symbol for magnesium sulfate, I'm going to erase this real quick. Magnesium sulfate, we're going to get MgSO. Oh, that should be a sulfate, SO4. We'll learn the difference between sulfate and sulfite. It's not really important right now, but I want you to understand if you have a +2 and a -2, the 2's are going to cancel out, so you don't have any subscripts. But for zinc 2 nitrate, zinc, the Zn has a 2+ charge here. And then your nitrate is an NO3 with a -1 charge. So the 1, understood 1, is going to cross over and be the subscript for zinc. And then the 2 is going to cross over and be the subscript for the nitrate. So your formula is going to be Zn, open parentheses, NO3 with the 2 on the outside. So that's the complete ionic formula. So polyatomic ions are going to be very important to be able to, identify them, because if you have a subscript other than the number 1 on the outside here, you have to have parentheses. You have to tell me there are 2 complete nitrate ions. And whenever we draw Lewis dot structures, you will definitely understand why that is very important. So a list of common polyatomics that you need to start memorizing. You will have a quiz over these polyatomic ions. So make sure you start making flashcards and you're able to identify the polyatomic ion with the name. So we're just going to practice more writing the formulas. So looking on a periodic table, manganese has the formula Mn. The 2 says it's a 2+ charge. Your carbonate, so we go up to the CO3 with the -2 charge. The 2's are going to cancel out because you cross over the 2's, so they're going to be understood 1's, so you get just MgCO3. Potassium phosphite, the ITE, potassium symbol is K with a +1. The phosphite going over to the far right column, we get a PO3 with a -3 charge. So we cross over the 3 here, the 1 crosses over on the outside, so our formula is K3PO3. And don't forget that if it's an understood 1 on the outside of your phosphite, you don't have to write parentheses. So then iron 2 dichromate, let me erase this down here, get some more room, and it's not erasing. Iron is Fe with a 2+ charge. The dichromate come over to the middle column, which is Cr2O7 with a -2 charge. So your +2 -2s, again, they're going to cancel out. So we get FeCr2O7, and I don't need parentheses around my polyatomic because it's understood 1. But barium thiocyanate is your last problem, where you have Ba with a 2+ charge because it's in group number 2. Thiocyanate is SCN with a -1 charge. This is a situation where you're crossing over an understood 1, but then there's a 2 that needs to go on the outside of your thiocyanate. So we end up with Ba, understood 1, open parentheses, SCN with a 2 on the outside. So this would be your formula. This is a situation where you have to have parentheses around your polyatomic because your subscript is something other than the number 1. Okay, so for covalent bonding, it's a little bit simpler. Covalent bonding is a compound that forms between 2 or more nonmetals. So there are no metals in the formula. That's an extremely important concept that you need to remember. And they're formed by covalent bonds, which are bonds that are shared between the 2 atoms. So there's no transferring of electrons. There are no charges. So on the bottom, no charges. Okay? No metals and no charges. And these compounds are known as molecules. Diatomic molecules, these consist of 2 atoms, and these are completely stable. They naturally exist due to their increased stability, and they contain 2 atoms, but they're still considered an element. So the element of hydrogen will never exist by itself. It'll exist as 2 together because it's more stable in that manner. So these are a list of your diatomic molecules. You need to memorize these diatomics because they will be very important for reactions in the future. So you need to memorize all 7 naturally existing diatomic molecules. So then whenever we use to name and write formulas, we're going to be using this prefix chart. And the only rule that we have to remember is never use mono with the first element only. So if there's only one element of the first molecule, we never say mono. For example, carbon dioxide. We don't say monocarbon dioxide, we just say carbon dioxide. You don't have to write mono with the first element. So if we just remember these prefixes, where 1 is mono, 2 is di, tri, 4 is tetra, 5 is penta like a pentagon, 6 is hexa, 7 is hepta, 8 is octa, 9 is nona, 10 is deca. And you need to write this in your ISN, and we're going to be practicing naming and writing formulas for covalent compound because it's all based on this prefix chart. The next unit, part 2 of this lecture, will be all about ionic compound naming. Okay, so practicing writing covalent formulas and writing the name. Again, the only rule is we don't use mono over the first element. So if you don't see any prefix, then oxygen is just O with a 1. The difluoride means there are 2 fluorine atoms. There's no cross and drop with covalent compounds. That is the biggest difference. And we know these are all covalent because there are no metals in these formulas. So then the disulfur, di represents 2, so there's 2 sulfurs. Deca oxide, so that would be a O with a 10 because the deca represents the number 10. Sulfur, there's no prefix, so it's an understood 1. Trioxide, 3 oxygens. Sulfur, again, there's no prefix, so it's just an understood 1. Hexafluoride, the hexa represents a 6. So you literally write out what the formula says. There's no cross and drop. So going back, writing the name, if there's an understood 1 for the nitrogen, we don't use the mono. So it's just nitrogen. The 3 represents 3. trihydride. Everything's going to end in IDE. The 2, the disulfur. Okay, there's no IDE formula for the first element. The 2, dichloride. So the only changing, or the only ending that you change, is at the second element. The 2, dinitrogen, was this trioxide for the 3. And then phosphorus, there's an understood 1, so we don't use the mono, we just say phosphorus. And then the 5 is the pentachloride. So for covalent, it's just the name, prefix or no prefix, plus the element ending in IDE. So we don't change the first element, we only change the ending of the second one. But mostly for covalent formula, if you know that there's no metals, we use the prefix chart, there's no crossing and dropping, and then whenever you're naming, the only ending that you change is for the second element only. The next lesson, or the next part of this unit, is going to be all about ionic compound naming, and it's very intense because there's a lot of information that we have to remember. With this lecture, we're going to practice ionic compound formula writing, and then we'll do the naming next time. But for covalent, straightforward, we use the prefix chart, and we'll practice this all in class. All right, so have you accomplished the objectives? We should be able to understand what metallic bonding is and how it leads to metallic properties based on the electron C model. Understand the difference between an ionic and a covalent compound. That's if there's a metal or not. And then writing the formulas for ionic and covalent. And then the only naming we did today was with covalent bonding. The next unit, or the next part of the unit, is going to be all about ionic compound naming. So just writing the formulas for ionic and covalent, and then being able to name just a little bit of your covalent compounds. Please write down any questions that you need to ask me in class, and we will hopefully take care of all the information when the next time we lecture about this.